Hi, I'm Glenn Whitney, president of the National Museum of Mathematics, and we're here in the Dallas Arts District today with walkSTEM so that we can look at the world through a mathematical lens. We're going to be visiting places like the Nasher, the Wiley Center, One Arts Plaza, and more, looking at the art, the natural world, and the architecture of these buildings in a way that will allow mathematics to bring out some of the hidden surprises inside. We're going to start right here at the Winspear Opera House, and it's a great place to begin a math tour because we'll see that the architects, Foster and Company, were literally playing with numbers when they built this structure. And there's lots of different mathematical characteristics. If you ever happen to get a view from above the city, you'll see there's a giant hexagon in the sky on the roof of that. We can't really see it from here, so we're just going to start with one aspect of the building that you can see very well from right here, which are these louvers up overhead. And you know, you might expect, for example, that in a grid like this, you'd see the same number of louvers in every rectangle, but as you look around, you'll see that's obviously not the case. So we're going to try to take a little look at what's going on there. But first, we'd like to understand a bit about the louvers themselves. For example, how big are they? Let's just think about their length. You know, from one end to the other of each one of these individual louvers, each one of the flaps that moves up and down. And we would like to use some mathematics to help us, you know, understand them. So how long do you think they are? We might start by guessing. How long do people think those louvers are? Just take a look up there and kind of guess.
20 feet.
I hear 25 feet, I hear 20 feet. Okay, fine. But we want to try to be able to do better. So how can we, now I brought a tape measure. And unfortunately, although I am wired for sound, it doesn't quite give me the ability to fly up there and put the tape measure across one of those louvers. So how could we, you know, we can't get up there, but how can we measure that louver exactly?
Use the windows. Measure the windows.
Okay, so we want to have them stand underneath the ends of the louvers. And why will that be useful?
From here, start and then end.
Yeah, right. So what we're actually relying on when we do that is, you know, whenever you're going to do math, you should have a whiteboard with you. What we're relying on for that is that we're going to create a particular shape, and we're going to use the mathematical properties of that shape to help us do the measurement. So here's the louver, way up here in the air, okay? And here we are on the ground, and we would like a line that has the same length on the ground that we could actually measure. So what shape would we like to make out of this? That we're going to be able to have that property.
A quadrilateral.
A quadrilateral? So will any quadrilateral do? Will I be able to? No, I need a special kind of quadrilateral. What do I need?
2 parallel lines.
Yeah, right, exactly. So actually any parallelogram would be good enough because a parallelogram has the property that opposite sides are equal. But what's the most convenient parallelogram for us to make? The most convenient kind of parallelogram for us to make? A rectangle. So what we'd like to do is make this into a rectangle so we can find these 2 points. We'll measure the distance here, and that'll give us the length of the louver up above. Okay, fine. How are we going to be sure that we're right underneath the end of the louver? What can we do down here on the ground that's going to make us certain that we're underneath the louver?
We have markers on the window.
Yeah, exactly. We can actually see right here at the base of the building where in fact, here's our rectangle right here on the building that we're going to use. And so we can see that this seam in the concrete blocks, and over there, that seam over there, not the nearest seam, but one farther over, that's exactly the length of those louvers up there. And so now we can just measure it right on the ground. And if I have a friend to help me, somebody, here we go, thank you. So we're going to go right from that seam. And I tell you what, we're going to assume they made the blocks the same length, and we'll just measure one block. So get that right down onto the block. And here we go. And it's 14 feet. And so how long is each louver?
28.
28 feet. So actually your estimates are pretty good. Well done. All right, so now we have a sense for the louvers. They're each 28 feet. Now, can we try to get some sense of what's going on with these numbers of louvers? If you look at adjacent cells, so they have these rectangles that got a long direction and they've got a short direction. The short direction is the length of the louver. So look at ones that are side by side along along one of their long edges in terms of these rectangular cells up above. What do you notice about the louvers between two cells?
They vary.
Yep, obviously we're seeing different numbers of louvers in different cells. What else do we see? So in some cases, if they close, it would actually touch. So not in like the cell over there that only has 2 louvers, those are never going to touch. But in some of these other cells, they might touch or even overlap. Yeah, excellent observation. What else do you notice about louvers in 2 adjacent cells?
They're attached to the same position.
Exactly. Anytime you've got one louver, you know, if there's more louvers in the next cell, the ones from where there's fewer louvers go right through and attach in the same axis. So that actually tells us something about the numbers of louvers that could appear, because each one of those louvers from the cell that has fewer goes straight through. So I'm going to draw on here as if I had a couple of cells. So here's one cell, and here's the next cell. And like if I take this one that's got 3 louvers across, well, we know these continue. So we're going to have at least 3 louvers over here. And so you'll see there's 3 and then 3. But then there's more in the next cell. And how many more? Could it be an arbitrary number of more? What do you notice about the way the louvers extend into the next cell?
They're in between them.
It's always in between, and I heard doubles. So now if I put 1 louver in between each of these louvers over in this cell, will that double the number? In other words, does it go from 3 to 6? Take a look up there. 7. Why does it go from 3 to 7 if you're putting 1 in between each? Why wouldn't that be double? Yeah, because if you draw 3 lines in a rectangle, it breaks it up into 1, 2, 3, 4 spaces. So you actually will be getting 3, if I want to do it here, you'll be getting 3 plus 4 times 1. Where did that 1 come from? Because you added 1 in every space. Can anybody see a place where a different pattern was used to move from one cell to the next? Yeah, what do you see over there? Yeah, inserting tube in every space. So, so we start over here with 2, and then what happened is those continue into the next cell, and we have 2 added in every spot. Okay, and so now we get the number pattern that we go from 2 to 2 plus 3 times 2, which is equal to what? It looks like 8. Okay, excellent. And you'll see, if you look here close to the building, the same thing is done with 3 of them. Okay, where these continue, and then we add 2 between every one of those, and so now we're going to get 3 plus 4 times 2, which is what? 3 plus 4 times 2, 11. Excellent. But now if you look way down at the other end, some of you may have trouble, may block from the tree. You'll see from the other direction, we take these 11, and it actually lines up with 5 on the other side. And we put 1 in between each. So we can see from this direction, we're getting 5 plus 6 times 1 also equals 11. So you can see that the architects are playing with numbers and different ways of breaking down the same number using simple elementary arithmetic. So it's kind of fun to see how we start with 5 on one side and 3 on the other, and then using these 2 different ways of sticking extra slats in the middle, we come together to form the number 11 in the center. So I think that's something that the folks here will enjoy, to think about the different patterns of numbers that were used to create this building. And now we're going to head on over toward Booker T. Washington School down in the corner. Okay, just keep filling in this way until you can all see the statue of Pegasus here on the grounds of the Booker T. Washington School for the Visual and Performing Arts. You know, connecting mathematics and the arts, I think, is something that enriches both subjects. And part of the point of these walks is to try to open people's eyes to looking at the world in a mathematical way. So here we have a statue of a sort of familiar form as associated kind of with Dallas. It was obviously a long time as a Pegasus sign on the Magnolia Oil building. And so I think that's part of it being used here as a symbol for Dallas. But if we take a look at this through a mathematical lens, we can say, okay, Pegasus is a very complex, flowing form, and you know, it's a very dynamic sculpture. The horse seems to be caught just in the midst of launching into the air. And yet, this had to be constructed by the artist out of these pieces of steel, and although you can see that some of the individual pieces of steel are very complex, especially in the mane where the wind seems to be rippling through the mane, we can also look at this and see some very simple, very basic shapes that the artist was able to use and incorporate even in something as complex and flowing and free-form as a horse. So looking at this, what basic shapes would you see? Yeah, there are triangles. You might see some, for example, in the neck, forming the contours of the neck. What other shapes? Circles, yeah, right at the horse's, I don't know, hip, or whatever you would call that. We see pretty much a circle made of steel. What else? Sorry? Cylinders, absolutely, especially in the wings. Some of those are just essentially half pieces of pipe that are used to make those wings. So the main point here is that when we look at the world, we can break it down into basic shapes, and it'll help us understand the structure of things and recognize that those forms make up everything around us, and also they tell us something of the purpose. We see a circle at the rear hip of the horse because that's a joint that has to rotate the way that a circle can easily rotate. So we can understand the functions of things in the world around us through their basic mathematical shapes. All right, our next stop is over at the Wiley building there. We're going to stop just at the top of the ramp system, heading down into the main entrance of the theater. Okay, so this is a rather grand entrance to the Wiley Theater Center. And we see there's a whole system of ramps heading down toward that building. There's the ramp that we're standing on right here, and there's this zigzag system of ramps just to my left, your right. And what we want to understand here is we want to compare those two ramps. And one of the basic ways that we measure a ramp when people are building ramps like this is they talk about the percent pitch. And so we'd like to take a look at percent pitch here. And it might sound like a complicated term, but it's not. It's something we can break down easily even for elementary students. We want to compare the number of inches that the ramp drops for the number of inches that you travel horizontally, parallel to a level earth, not along the ramp, but horizontally. So we're just going to compare the number of inches that you drop for the number of inches that you move across, and we're going to express that as a percentage. So what we'd like to figure out right now is how can we calculate that for these two ramp systems. How should we calculate that for this ramp we're standing on, and how should we calculate it for that ramp there? Any suggestions? Yeah? Okay, we could try to use the cylinders. If I knew how these cylinders lined up with each other, then that would certainly work. That's a great idea. What else? Yeah, we've got a lovely grid right here. So if we can just measure the number of grid points across until we go one grid unit down and measure the grid unit, we'll be in good shape. So we're going to do that right now. Somebody want to give me a hand? Okay, very good. So find a hole that's right at the ramp level, because we want to find a hole that's exactly where at the ramp level. Yeah, but we want to line up with the holes because the other things in the grid. So can you find a hole that's just right at the surface of the ramp? Might be in front of or behind you. Like they say on an airplane, the proper exit may be, okay, yeah, that one looks good right there. And now we're going to go till the next time when one shows up right at the grid level. And look, it's right here. So we're going to measure this across, and it's 115 inches. Somebody making a note of that? Okay, 115 inches right across. And now all I have to do is measure this up and down, and that's 16 inches. So that's 16 out of 115. We want to express that as a percentage. So what we have to do? We want to get it, over 1,000 or over. Oh, you've got it. Okay, wonderful. Pull out the phone. Just tell me, and I'll repeat it for the.
The percentage is 13.13.
Okay, so we calculated that fraction, 16 over 115. It was 0.13 something or other. Convert that to a percent. This is a 13% ramp. All right, excellent. We did a great job. How are we going to do this one over here? And you can come on over and take a look at this ramp system. And please use caution when you step from the one ramp onto the other, because in some places there is a height differential. How are we going to measure the pitch of this ramp? Same way. Okay, where should we measure from? I don't see any holes over here. Okay, we'll go to the end there, and we'll measure. Where will we measure over there? We could choose a point, and then we have to try to find the same point at the same level over here. So, what assumptions do we need to make to be able to find the point over there that's going to be the same level as over here? I'll give a clue. Do you think that the slope on this ramp is the same on the slope on that ramp? Okay, so right here is where the two ramps meet, right at that point right there. If the slope's the same, where would the same horizontal level be over here? If the two ramps are sloping at the same slope, and we can have the level where they meet over there, where's that level going to be over here? In terms of this vertical line, where on this vertical line should I hold my tape measure? Halfway, midpoint, right? If they're sloping at the same rate, this one slopes up the same as that one slopes down. So I wanted to find the midpoint of this wall, and that's where I would measure to. So I can measure the height of the wall right here. It's 32 inches. So the midpoint will be at 16. And unsurprisingly, that hole right there is at 16 inches. So now I just need to measure across from here. Again, I'll need somebody to run on over. Time is, yeah, exactly. Thank you. Okay, sure, I'll hold it. Excellent. And it's not going to be long enough, so pick a point that you can reproduce where you are. And again, pull it tight. We don't want it set. Yeah, nice.
211.
Okay, 211 plus 182 is 393. Did I do that right?
Yes.
393. The drop was how much? 16 over 393. What percentage are we getting now? Yeah, so I see some folks with their ever-present pocket computing devices.
0.04%.
Okay, so 0.04, which we express as a percent, is 4%, less than 1/3 of the pitch of that ramp over there. Why is that important? What's the purpose? Why not just have all the ramps be 13%? Or all of them be 10%, or whatever it might be? Accessibility, right? So an important message here is that mathematics, and using that mathematics to design the geometry of these ramp systems, serves everybody. And it's a tool that we use for social equity as well as for engineering. So I think that's a really important message to get across. Okay, our next stop is going to be over there at the Dallas Sculpture Walk in the Hall Art Center. So the Sculpture Walk here behind me is a really lovely spot. A number of beautiful pieces that really have a lot of mathematical ideas and structures embodied in them. But what we're going to do today right here in this spot is we're going to go on a mathematical fossil hunt. So this image, and if you can't see it super well, do feel free to come a bit closer and take a look. This is a fossil, and most fossils, as we know, are remains of creatures that lived long ago. You might see the first bird lizard, Archaeopteryx, with its wings embedded in the stone. But this is a fossil of mathematics. Now, what could that possibly mean? I'll tell you about it, but first what I need you to do is look around you in this area here and see if you can find this fossil pattern reproduced somewhere right in the immediate area that we're standing right here. Okay, I see lots of people pointing right away. You've already seen it in the bottom surface of this fountain slash stream running along the landing here. There's this same ripple pattern, and it shares the same essential characteristic, which is that the upstream ripple, which is this side here, the upstream is very shallowly sloped, and the downstream is very sharply sloped, just like what's been built on the bottom of this stream here. And what this actually is a fossil of the sandy bed of a stream. And the reason I call it a fossil of mathematics is because we know that water, as it moves, tends to oscillate. And mathematics is something that will study how that oscillation works. As you know, waves are one of the important objects of mathematical study. And it tells us that it's going to create forces on the bottom of the stream. It will create this type of ripple pattern. And moreover, that ripple pattern influences how the water moves. And so it reaches an equilibrium, another thing that we can study mathematically. And that was captured in this fossil. And it tells us that the laws of mathematics were the same hundreds of millions of years ago as they are today. And moreover, a modern architect can imitate this ripple pattern from nature, create it here artificially, in order to make this stream move the way water would in a real natural stream, and create and enhance the more naturalistic environment even here in this urban setting. All right, we're going to now head on over. We're going to be continuing to head along Flora toward the Dallas Museum of Arts. As we're walking along, just to be things you can be thinking about as you're walking through an area like this, we talked in the Pegasus sculpture about how you'll see basic shapes occurring in natural settings. You'll also see them in architectural settings. So for example, the Meyerson Symphony Center to our right was designed by I.M. Pei, and he quite consciously used two very basic shapes to enhance the structure and create a sort of dramatic tension, namely the circle and the square. So if you look at that building, see if you can find the places where there are both circles and circles embedded in squares that sort of heighten a sense of contrast and drama for that building. And it is my feeling that in a math tour, especially a math tour for younger kids, it's a great idea if you can have the tour have at least one really big number, right? There's something sort of exciting about really big numbers. So if we look around the space here, does anybody see a really big number that's sort of crying out? Yeah, I see everybody pointing right down here. I mean, I don't know about you guys, but I look at this like, how many stones did they need to use to make this thing? And it runs to the end of the block. Now, obviously, this is a case where we're not going to be able to get the exact number of stones. First off, they had to take a few out for the trees and so on. But mathematics isn't only about exact answers. It's also about estimating and understanding the world through estimation. So, what are some suggestions for ways that we could estimate the number of square blocks that are used to create this plaza all the way to the end of the block? It's an array, right? It's a rectangular array. So our basic approach is we're going to count across here. And if a couple of you could independently count the length of this row so we can compare answers and hopefully get something that's reasonably accurate. So that's going to work. Now, are we going to count all the little tiny blocks all the way to the end of the? No. So I hope a couple of you are doing this count. No, we're not going to count all the blocks all the way to the end of the block here. So again, how can we estimate that number? Yeah, we're going to multiply again. This shows how powerful multiplication is. We're going to use these big, we could use these little squares, but we're going to have a better time if we use these big squares. So I need somebody to take one full big square and count how many of these little squares make up one full big square. So if a couple of you could do that. And then I need some more of you to start going down the block and count how many of these big squares you pass. And I'm going to rely on you all to keep those numbers. Don't try to keep two of them. If you did this, don't do the others. If you're doing this count here, don't do the others. If you're doing this count along here, don't do the others. At the end of the block, we'll do our calculation. So it's a big, long rectangle. And we're going to first try to get an estimate of the number of stones long this whole thing is. So who counted the number of stones per big sidewalk block? Did that?
26.
Oh, yeah, okay, 26, I'm hearing lots of 26s. Okay, so we have 26 little stones per big block. Okay, so here's my calculator. All right, 26 of those times how many of the big blocks were there?
18.
I heard 18,
Oh, we have it 14 and a half.
14 and a half. Did we get any other numbers? Okay, well, let's say 16. That's in between the different, we have two different data points, so we'll take right in the middle. So 26 times 16 is 416 blocks long. And now what counts do we get for the number of blocks along a short side here? 45? 45, I'm hearing consensus on 45, so I'm gonna multiply that by 45. And I get 18,720 as our estimate for the number of little blocks here. That is a bona fide, really big number. And it's just amazing to think about the stack of 18,000 blocks high. If each one of these blocks is only 2 inches tall, let's say, I don't know how, I didn't dig one up, so I don't know. Let's imagine it's only 2 inches tall. So times 2, that's 37,440 inches. I'm gonna divide that by 12. That's 3,120 feet. That's more than half a mile into the sky that these blocks would go if you stacked them all up like a tower of blocks. I think that's pretty exciting for kids. All right, our next stop is over at the Nasher Sculpture Center. So any thoughts about aspects of this bamboo we might measure?
You could count the leaves, like the spiral.
Absolutely, we could look at where the leaves branch off, or how the leaves are arranged on any one given branch of the bamboo. That might tell us something interesting about the bamboo. What else?
The segments and intersections.
Yeah, this is a nice plant, and then it has some very obvious characteristics that are amenable to measurement. So we could measure the length of the segments and see, are they relatively constant along one stalk of bamboo, or do they vary a lot? What else might we measure? Circumference, right? I brought strings so we could measure right around each one of these. And then what kind of a relationship might we look for? Yeah, a difference in the height of those segments versus the circumference of the bamboo. And if you just look here, if you eyeball it, I think you will see that on the pieces of bamboo with a larger circumference, the segment length tends to be longer. And we could look, is it a linear relationship? Is it some kind of a curve? Is it always the case that the thicker the bamboo is, the longer the segments? And begin to understand the structure of how the bamboo grows. As we're walking by the stand of magnolias, we don't really have time to stop right now, but do take a moment to look carefully at one of these beautiful glossy leaves of the magnolia tree. And what you will find is that there are certain shapes formed by the veins of the leaves create sort of geometric shapes. And what you'll see is that same shape repeated over and over again, getting smaller and smaller as you head toward the edge of the leaf. And understanding that kind of repetition and the fact that you can have a pattern that repeats at smaller and smaller scale is something where mathematics has allowed us to understand the structure of living things around us, understand why they're formed that way, much more clearly. So it enhances our appreciation of the natural world around us as well. What we're going to be talking about is this simple piece of playground equipment. Or actually, it's not so simple. If you take a look at it, it has a very intricate structure. It's formed out of these beams that are connected by the red spherical hubs. And there are exactly 5 beams meeting each hub. And the shape formed by any 3 of the beams is always the same. It's sort of a triangle. And thousands of years ago, a fellow named Plato said, well, what are the most regular ways that we could put basic shapes together like triangles? He said, well, we want to have the same number of shapes meeting at every corner, or vertex as mathematicians call it, and we'd like every shape to be the same. So we might, for example, get this little triangular pyramid, also called a regular tetrahedron, and he discovered there were a number of different ways of doing that same thing. So for example, you might have 12 regular pentagons and get this shape called a regular dodecahedron. And the most complex way that he found to do it was to take 20 of those triangles and stick them together to form this shape called a regular icosahedron. It's got 20 identical triangular faces, and I've done it in a bunch of different colors here to highlight that. And so this is one of those 5 platonic solids that he discovered. And this structure holds an actually even more intricate treat right in the center. You'll see there's a network of ropes that the kids can climb on in there. And at the very center of this structure, if you look, or if you climb in there, as I've been dying to do, it creates another geometric structure, which is this one. It's gotten a little bit beat up with all of our travels, but I'll pop it back out here for you. And so we're gonna get a more solid model that you can use on the tours. This is called a well, it's called a soccer ball by some people. It is the shape you see on a soccer ball. It's called a buckyball by chemists because it's the structure that the carbon molecule C60 takes on. Or a mathematician would call it a truncated icosahedron. And this is mathematically, I said this may be the most mathematical object. Why did I say that? Well, what is the most symmetric possible three-dimensional object? What three-dimensional object has the most symmetry of all? Sphere, yeah, exactly. It makes you very happy because you can turn it any amount in any direction and it still occupies the same volume of space. So it doesn't change when you do any of infinitely many transformations. Now the interesting fact is that there's a second place. There is objects that have the second most symmetries. It's not any possible amount in between. And this truncated icosahedron is one of the objects that has the most possible symmetries of anything except the sphere. We can see that I have this vertex at the top and the pentagon is pointing right toward me. But now I can pick any other vertex, say this one. You could have picked any one you want. I can move that one to the top and again have the pentagon pointing right at me. And so again, I've transformed the object, but it is still occupying the same volume and space. So each one of those is a symmetry. So I get one symmetry for every corner of this. It turns out this has 60 corners, so that's 60 different symmetries. Plus, I can always take a mirror and reflect it in a mirror. That doubles the number of symmetries. So this has 120 different symmetries, and it turns out that number 120 is the record. It's the most number of symmetries that any object other than a sphere can have, and we have a chance for kids right here to absorb that and explore that and learn about the symmetries of this very interesting shape just as they're playing here on the playground. All right. I want you to just take a look at the Hunt oil building on the right, and you'll see that it's formed out of 2 cylinders. There's a vertical cylinder right at the middle, and then there's a much larger radius portion of a horizontal cylinder. And where they intersect, it creates this very interesting and I think very beautiful swooping curve in space. So it's one of the great things about mathematics is we can create beautiful complex things out of very simple building blocks. Speaking of building complex things out of simple building blocks, our last stop is going to be this artwork to our left at the Dallas Museum of Arts. It's a mural called Genesis, the Gift of Life. And we're going to look at it first from a distance, then close up, and then we're going to move back out and hopefully get a little bit of a new perspective on it from a greater distance again. And I want to give everybody a chance to get up close and personal with the mural before I move on. But we do have to wrap now, so I'll keep it quick. So what I noticed when I look at these boundaries is the place where I saw a high contrast boundary, the edge of each tile lies right along that boundary. So the macroscopic structure of the sharp boundary has influenced the microscopic structure of how each individual tile lies. Whereas I saw a color gradation basically along here, but when I look up close, I can't see that anymore. I've somehow lost the detail and the individual tiles don't seem to have any relationship. So the basic moral here is that when you build something large out of small pieces, that macroscopic structure has a profound influence on how the microscopic structure has to line up. And that's a theme that recurs throughout mathematics. Now, as we walk back out, I want you to pick a region that's of a fairly uniform color, and just take a look at how that looks when you're looking close up. And then we're going to walk back over to the awning, and I want you to then look at that same region from a distance. So from here, and we're just about wrapped up, when you look back at the region that you were looking at, I think what you'll see is more of an overall impression of a single color rather than from close up we saw one individual color. And so that brings us to the question of color mixing, which is obviously very important in the arts. And we get this diagram that some of you may be familiar with, the color wheel. And we can use it as a tool to understand adding color. And you could ask, is adding color something that has anything to do with mathematics, or is it just that we're reusing the word? And the answer is no, it can be analyzed very mathematically, and we can use the mathematics to help us appreciate the art and the color they're in. So for example, in this color wheel, if we want to add up two colors, we can imagine there's a center point and the colors are at different angles. And if we want to know how to mix two colors, we take the angle bisector of that angle. So that's a basic math concept, which is now telling us something about the colors in this art. But you can see this, like any model, that's what we use mathematics to model the world, and any individual model has, shortcomings, because the real world is extremely complex and there's always another layer of complexity. We can always make our model more accurate. So this angle bisector model has some problems. If I want to mix blue and orange, well, that's a straight angle. So now all of a sudden, like, there are two angle bisectors, right? There's the one that's going to come off this way and the one that comes off that way. Which one would we pick? Well, is orange and blue together make yellow? No, I don't think so. Does orange and blue together make magenta? I don't think so. So there's obviously a breakdown in the model there. It only goes so far. And in fact, if you want to do something like maybe make a laser printer on which this color was printed, obviously the customer wants the colors to look like the colors that they thought were going to appear. And so you need to have a much more advanced model of color, a mathematical model of color, so you know how much of the different toners to put down. And so that led to this little piece of mathematics, which very sadly I don't have time to go into the details of. This is called the Kubelka-Munk equation. And this equation is literally from a paper written at Xerox when they were first inventing laser printers, so that they could calculate how much of the different inks. So there's a lot of mathematics that goes into something as simple as printing out a color wheel on your laser printer. All right, I hope you enjoyed. I have to run back to the beginning to meet the next group, but you all can enjoy, chat. Plenty of time for you to make your way back if you're able to come to the presentation later about how to construct math tours. So thank you all. It's a real thrill. I'm sorry to have to run.